Okay, so let's look at lesson 2.3 here. In lesson 2.3, we're introduced to this concept called the fundamental theorem of variation. Now, before we describe what that means, I think it's easier to discover it on our own. So let's look at this equation, y equals x squared. And we're going to substitute these numbers in for x. When I square 1, we know that that answer is going to be 1. When I put 2 in for x and square it, we're going to get 4 as our answer for y. When I put 3 in for x and square it, I'm going to get 9 for our answer for y. Now the idea in this lesson is we want to look at what's going to happen to y if our x gets doubled. Now you might at first think, well, if x is going to be doubled, then y is going to be doubled, which might be a fair assumption, but let's see what really happens. So first, if I double my x's, so if I double 1, I'm going to get 2. If I double the 2, I'm going to get 4. And if I double the 3, I'm going to get 6. So I'm going to take and put those numbers now into my equation, y equals x squared. So when I square the 2, I'm going to get 4. When I square the 4, I get 16. And when I square 6, I get 36. So again, the question is, what happens to y if x is doubled? So now let's look at our values for y. When we doubled our x's, our y's went from being 1 to 4, from 4 to 16, from 9 to 36. In other words, the y is multiplied by 4. Let's look at the next one. What if we were asked the question, what happens to y if this time x is tripled? So going back to original values for x, let's triple each of those values. So if I triple 1 or multiply it by 3, I get 3. If I triple 2, I get 6. And if I triple 3, I get 9. So when I plug these numbers in to my equation, I'm going to end up with a value of 3 squared, which is 9, 6 squared, which is 36, and 9 squared, which is 81. So let's compare these values for y now to see what happened to y when x was tripled. Went from 1 to 9, from 4 to 36, and from 9 to 81. So if you notice this time, y is multiplied by 9. So before we go any further, let's look at what we just discovered. So ignoring the tables, when we doubled, so looking at the equation y equals x squared, when we doubled the x, y was multiplied by 4. When we tripled the x, y is multiplied by 9. Now remember, if I double something, that means I multiply it by 2. If I triple something, I multiply it by 3. Now look at what we're multiplying, and look at what we're multiplying x by, and look at what we're multiplying y by. Look for a relationship there. What you should notice is that if I square 2, I get 4, and if I square 3, I get 9. Well, where do we get that squared from? Right here. So that squared told us what happened to the x here. The same thing happened to the y to the second power, which is pretty much the fundamental theorem of variation. So what's in purple here? This is what your textbook, this would be the technical definition for the fundamental theorem of variation, which states if we have an equation in this form, y equals k times x to the n, meaning it varies directly as x to the n, and x is multiplied by some number. Now in your book they're going to call it c, but really it's any number. Then y is multiplied by that number to the nth power. And again, we get that nth power from our equation. Another way I like to look at it is, remember direct variation. If x increases, then y also increases. Or if x decreases, y also decreases. So in other words, in this situation, whatever happens to x, the same thing happens to y to the nth power. Okay, so if x gets multiplied by 2, y is going to be multiplied by 2 to the nth power. If x is divided by 3, y is going to be divided by 3 to the nth power. So whatever happens to x, the same thing happens to y to the nth power. Let's look at the next example, or the next part of the theorem. It states that if we have a situation like y equals k divided by x to the n, you should recognize that's inverse variation. So if y varies inversely as x to the n, and if we have x multiplied by a number, again they use the letter c here, then y is divided by c to the nth. Because remember, inverse proportion, remember If x is increasing, then y is going to be decreasing. They're opposites. So another way to look at it is when we're dealing with inverse variation, whatever happens to x, the opposite happens to y to the nth power. So if x gets multiplied by 2, y is going to be divided by 2 to the nth power. Or if x is multiplied by 3, y is going to be divided by 3 to the nth power. Let's look at some other examples to maybe make more sense of this. Suppose we have the equation, or suppose y varies directly as x cubed. What happens to y if x is doubled? So if we were to write out a variation equation, remember varies directly means we're going to take k times something, so it's going to be y equals k times x cubed. So when I look at this, when x is doubled, that means I'm multiplying it by 2. So since it's direct variation, whatever happens to x, the same thing happens to y to the nth power. Well, 2 cubed is 8. Now we don't want to just say our answer is 8. That doesn't tell us anything. Our answer is this. Y is multiplied by 8. You want to make sure that you don't say y is multiplied by 2 cubed. Technically, there's nothing wrong with that, but it's always best to go ahead and simplify it. So we would say y is multiplied by 8. Let's look at the next one. Suppose y varies directly, again it varies directly here, as the fourth power of n. So it's the reason why it's nice to set up an equation, if you look at this, now the previous one it had x cubed, so it was easy to see what the exponent was going to be. Sometimes if you're just planning on just looking at the variable, you might notice that there's no exponent, but it's supposed to be the fourth power of n. So it's just good to be in the habit of writing out your equation. So we have s equals k times n to the fourth power. So the question is, what happens to s if n is tripled? Tripled again means that we're going to multiply it by 3. So if n gets multiplied by 3, since this is direct variation, s is also going to be multiplied by 3 to the fourth power. Well, 3 to the fourth power is 81. So that's how you get your answer. So s is going to be multiplied by 81. Let's look at a couple more. Suppose d varies inversely. Okay, you want to make sure you read these carefully. Don't just get in the habit of following one pattern here. D varies inversely this time, so that means it's going to be equals k divided by something as the cube of e. What happens to d if e is tripled? So d varies inversely, so it's going to be d equals k divided by the cube of e. So remember, since this is inverse variation, whatever happens to x, or in this case e, the opposite happens to y, or in this case d. So we would say d is divided by, and if it's tripled, that means it's being e is being multiplied by 3, so this is going to be divided by 3 cubed, or 27. And lastly, it says suppose L varies inversely. Again, it's inverse variation here. So we would say L equals k divided by the square of h. What happens to L if h is multiplied by 5? So what we're going to do is, since this is inverse variation, we would say that L is divided by 5 squared, which we know would be 25. Now that's pretty much it. Now I want to make sure that you understand that it's not that we're substituting, like in this last one, we're not substituting 5 in for h. We're looking at how our answer for L is affected if h were multiplied by 5. Just like in our example up here, we were looking to see how y was affected by the fact that x was going to be multiplied by 3, or how y was affected by when x is multiplied by 2. Now we could apply this to some story problems. So let's look at a couple here. Let's look at this first one. It says generally the weight of a land animal of a particular type varies directly with the cube of its femur diameter. Phoboromus, or however you pronounce that, an extinct rodent, is an ancestor of the modern guinea pig. Its femur diameter is 18 times that of today's average guinea pig. Estimate how the weight of this ancient rodent compares to the weight of a modern guinea pig. Okay, now story problems often can be intimidating, but I'm guessing that you were starting to get the hang of it when we were looking at these previous problems that weren't story problems. But it's really the same problem. They just added a bunch of words in here. Let's start at the beginning. They say the weight of a land animal varies directly with the cube of its femur diameter. So remember, our first step is to set up a general variation equation. So we would have the weight varies directly, so it's going to be k times something, the cube of its femur diameter. So I'm just going to use f cubed. So now if this extinct rodent, if its femur diameter is 18 times that of today's average guinea pig, we want to figure out how that affects the weight compared to the today's average guinea pig. So if we multiply f by 18, the question is, how does that affect w? Well, 18 cubed is going to be 5,832. Now that doesn't mean the weight of this extinct rodent was 5,832 pounds. What that means is that Phoboromus, its weight is 5,832 times heavier. So if you look at a modern guinea pig, let's say a modern guinea pig weighs, I don't know what they weigh, let's say they weigh around 2 pounds. You're looking at almost a 12,000 pound rodent. Can you imagine having to clean up the poop after that one? No thanks. Anyhow, let's look at this last auxiliary example. In a parade, the height of a float varies directly with the square of the length of the vehicle that supports the float. This year's vehicles are 3 times as long as the vehicles used 10 years ago. Estimate how the height of this year's floats compares to the height of the floats 10 years ago. So again, we want to start out with an equation. So here we have the height of a float varies directly with the square of the length of the vehicle. So our equation would be h is directly proportional, so k times the square of the length of the vehicle. So I'm going to say L squared. So if this year's floats are 3 times as long as they were 10 years ago, we want to figure out how does that affect the height. We would say today's floats are 3 squared, or 9 times taller. Now again, notice how I'm not just saying my answer is 9. You want to make sure that with story problems you always answer it so someone can read your answer and know how it relates to the problem. So that's it. Hopefully you understand it better now, and good luck.